In the last video, we finished up our analysis of the hyperfine interaction. So this was the interaction between the magnetic moments of the nucleus and the electron in hydrogen. And we have this perturbation Hamiltonian that was A over h bar squared S dot I, where S was the electron spin operator, I was the nuclear spin operator. And we were looking at how this perturbation, this interaction, when we include the magnetic moments of the nucleus and the electron, affected our levels in our hydrogen atom. And we focused on that n equals 1 state, which when we include these spin degrees of freedom is actually a degenerate state. So we applied degenerate perturbation theory to it, which essentially says we have to just diagonalize that perturbation Hamiltonian in the degenerate subspace, and that'll tell us how the levels are shifted and how the energy state eigenstates are changed. And we did that, so to get this, to diagonalize this, we had to put it in the matrix representation, and we had to choose a basis to do that. And we chose this, what we ended up calling the uncoupled bases. And we sort of wrote our basis vectors of that degenerate spin space like this, where these plus and minuses are referring to spin up and spin down, essentially the magnetic quantum numbers of the electron and the nuclear spins. And in that basis, we were able to figure out what this Hamiltonian was, diagonalize it, and we saw that the four sort of degenerate states ended up being, some of them were changed, and if we were to consider those, what ended up being the four degenerate states after we include the effect of that perturbation, they looked like this, where one of them, what I would call the polarized triplets did not change, and the unsort of polarized states, we saw that those got shifted into these two states, where essentially they were the symmetric and anti-symmetric combinations of those two states. So we saw that these were what those energy eigenstates sort of changed to when we included that perturbation. And the first order energy corrections were these three, what we would call the triplet states, because there's three of them that stayed together, all were shifted up in energy by what that constant was divided by 4. And this one was shifted down in energy by 3/4 A. So in terms of energy, our 1, 0, 0 ground state of hydrogen, when we include that hyperfine perturbation, shifted in energy, where 3 of them went up in energy, A over 4, and those were these 3 triplet states. And the singlet state dropped down an amount, 3 over 4A. So the total splitting of those energies was just A, and this was what we would call the singlet state, because there's just one of them. It's off by itself. And this is what our analysis showed. Today what we're going to look at is sort of, we did this whole process by using these states as our basis states when we wrote this Hamiltonian in the matrix representation. And then we had to do a bunch of work to diagonalize it and figure out what these states and what these shifts were. Now, had we had some insight, or if we had been, a little clever about this, we could have used these 4 states as our basis states for the matrix representation. And had we done that, those are the eigenvalues of this Hamiltonian, it would have been diagonal, and we could have just figured all this out by inspection. We could have just written this in matrix representation and picked off what those energy shifts were and identified that the states were our basis states that we were representing it in. So that's what we're going to focus on today. We're going to discuss, we called this one the uncoupled basis, and this is what we would call the coupled basis. Um, we're going to look at these two and sort of figure out and think about, why is the coupled basis sort of the good one that we might want to think about this hyperfine interaction with, and go from there. So let's think about the hyperfine interaction, right? It's this coupling between, we have two magnetic moments. We have one for, say, the nuclear spin, right, and one for an electron spin. And classically, what we're thinking about is just this has magnetic field lines that go like this, and some magnetic field associated with it. Likewise, this one does. And if I have this magnetic dipole in this magnetic field, I know it has, we went through this when we were deriving that Hamiltonian. I know it has potential energy that's the dot product between the magnetic moment of one times the magnetic field from the other, right? So there's some force associated with that, negative the gradient of that potential energy, and this force ends up exerting a torque, right? So the magnetic field from the nucleus exerts a torque on the electron and vice versa. So there's going to be some change in angular momentum associated with that, right? If we look at the magnetic moment of the individual particles, the proton and the nucleus, those aren't going to be conserved, right? There is some torque on particle 2 there, say, that is just going to be negative the gradient of negative m1 dotted with b2. And that torque is going to cause a change in angular momentum. Likewise, there's going to be one on T2. So what that means is, these torques mean that the angular momentum of the individual electrons and protons aren't conserved. Now, if I consider this whole system, though, my hydrogen atom, the net torque is still zero, right? Because the other torque is going to be negative d negative m2 dotted b1, and these are going to be just the same. Thank you, Newton's third law. But this these internal torques cancel, and the net torque on our system is still zero. So although the individual angular momentums aren't conserved, the total angular momentum is conserved, right? And this is kind of relates, to why the two different basis states, which quantum numbers say, were the good ones for analyzing this thing. If we map this whole sort of idea to quantum mechanics, these the individual spins, that ms and that mi quantum numbers, aren't conserved, right? They interact, they are coupled together. These uncoupled quantum numbers are going to be constantly changing because of that interaction. Whereas if we look at and define some total angular momentum between both of these things, that will be conserved. And the quantum numbers that we would associate with those conserved quantities are going to be sort of good quantum numbers, because they are going to stay the same as this system sort of evolves. And essentially what that means is, if we can define these total angular momentum quantum numbers, and they are conserved, what we're saying really is, if we think about it, let's say we define some operator that associates our total angular momentum, or any, in general, if we have some operator that like momentum here that's conserved, that means that it's going to commute with our Hamiltonian, right? Which means it's going to share eigenstates with that Hamiltonian. And this sort of comes into, that means it's a conserved quantity, because time evolution for these time independent Hamiltonians, you remember, hopefully we're all comfortable now with how that works. Those eigenstates are stationary states. So if these two operators commute, they share eigenvectors. Those eigenvectors are stationary states. those are good sort of quantum numbers we want to use. And it all ties together with essentially if we can identify what's conserved in that system, we have sort of a nice basis that we want. So, and that's essentially what we're going to look at today. You know, in the hydrogen atom, we can define for our system here some, we'll call it F, total angular momentum. That's just the angular momentum of the electron and the angular momentum of the proton. So the electron spin plus the proton spin, because remember we're looking at that L equals 0 state where there's no orbital angular momentum. This total angular momentum operator is, you know, it's going to have components that are going to be exactly what you would expect, right? Just the sum of the components of the individual spin operators, and likewise for Fz, Sz plus I Z, and it's an angular momentum operator. So if you think back to that sort of generalized angular momentum we discussed a few things a few videos ago, we're going to have the same sort of properties. It's going to have the same commutation relations, right, where we have I H bar Fz and the cyclic permutations of those. F squared is going to commute with all the components, right? Squared Fy F squared Z, and all of those are equal to 0. So it has those properties, and it's going to have, you know, this is going to have quantum numbers, F for total angular momentum, and a magnetic quantum number associated with the Z component of that total angular momentum, right? And so what we've got now is we've got an FM, a sort of total angular momentum basis or set of basis kets that come from considering the total angular momentum of our system. And we call that the coupled basis. And we call it the coupled basis because we are considering the system and the coupling between it and looking at that total angular momentum of that of all those parts coupled together. And to contrast that with our other basis we were looking at, which was the Z components of the electron and the spin by themselves, that was the uncoupled basis. And, you know, we called it the uncoupled basis because those quantum numbers in that we got from looking at the individual particles uncoupled to each other, just by themselves. If we had the spin of the electron off by itself, it would have stayed constant and been conserved, and this spin quantum number would have sort of described that. Likewise, for the proton, if we considered them uncoupled, we got a set of vectors that you know, could be used for that basis and would sort of stay constant and be nice, a nice simple description of it, and the coupled basis for when we consider the coupling between those two. So if we think, what are we doing here? All right, so we identified by considering our system what was conserved and realized, okay, we have these sort of are going to be the basis states we want to use to describe that system, and they're going to be our good quantum numbers. We sort of have to go through the process of, well, let's determine what those quantum numbers are. What are those actual basis states for this system, right? And these are essentially just the eigenvalues, or the kets that correspond to the eigenvalues of these operators. The you know, M associates it is going to result from that F sub Z operator, and F is going to be associated with F, well, more accurately, the F squared operator. So how do we do that? Well, the M quantum number is kind of straightforward, right? It's associated with that F sub Z operator, and even in the uncoupled basis, MS, ML, we know how this acts on that, right? It's just going to be SZ plus IZ by definition, acting on those two. That should be an S. Sorry, those two uncoupled basis vector, and we know the action of those two operators So that's going to be ms plus mi times h bar m s m I. And so we can sort of immediately see what this matrix representation is in the uncoupled basis. And this f sub z operator commutes with these operators, so we kind of expect them to have the same eigenstates. But f sub z in the uncoupled basis is diagonal, right? It's just going to have, well, if we're looking at the 1/2 system of our electron and our proton, for the up state, this is just going to be 1. For the up-down and the down-up states, they're going to be 0 and 0. And for the down-down states, that's going to be -1. And then we're going to have, zeros on the off diagonal. So again, in the up, down, up, down, uncoupled bases, we have a diagonal Hamiltonian. We know that. We know we've sort of seen that these are that our eigenstates are going to be similar. We've already kind of identified that these two polarized states are going to be the same sort of polarized states here. We do have some ambiguity though, because of this degeneracy. Or we have two eigenvalues that are the same for two states. So that means that any combination of those two states is also an eigenvalue for this operator. So we need to somehow distinguish which two states of any of these combinations are actually going to be the ones that make up the coupled basis we're trying to look for. But if we look at, so that's the f sub z operator. We know that in the uncoupled basis. The f squared operator, which is, the operator that's associated with this f quantum number, well, that one's not as straightforward, right? This is just going to be s plus I squared, which is s squared plus I squared, excuse me, plus 2s dot I. This, I just want to make an aside point, this 2s dot I, this is true because s and I commute. I've taken the two cross terms and just called them this and added them together. I can only do that because I know the spin operator on the electron and the spin operator on the proton commute, because one acts on the spin space of the electron, one acts on the spin space of the proton. But anyway, sorry, little tangential, but I thought it was important. So the question is, what is the matrix representation of this, right? And we already derived the S. When we were looking at our hyperfine interaction, we already kind of derived this operator, right? This was h squared over 4. If you go back to, I think it was the last video, 1, 0, 0, 0, 0, -1, 2, 0, 0, 2, -1, 0, 0, 0, 1. This was our s dot I operator that we derived previously. The s squared operator and these two operators in here, we can also sort of easily derive in our uncoupled bases, just because we know how the s squared acts on that uncoupled basis and the I squared acts on that. And what we end up with, I'll just write them off to the side here, is this s squared operator is 3 over 4 h bar squared, and this is going to be 1, 0, 0, 0, just the identity. I'm not going to spend my time writing all those zeros. So and likewise, the I squared operator is going to be the same, right? Because they have 1, zeros, zeros, right? Because the s squared operating on a spin 1/2 particle gives us that eigenvalue, and it's the same for any one of these states. So we have this matrix and this matrix and this matrix all in the uncoupled basis. We can just add them together and figure out that our F squared matrix, like I just said, is this plus this plus this. And what this ends up being is just h bar squared 2, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 2, 0, 0. So we have that in matrix form. This is kind of familiar to what we did when we solved the hyperfinite interaction there. It's block diagonal. So again, we are in this plus, 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 minus, minus, plus, minus, minus basis right now. And we can see that the sort of polarized states where both spins are aligned the same way are still going to be eigenstates. They're going to be basis states in this new basis, but we have this sort of block diagonal, this submatrix here that we have to diagonalize to sort out what our other two basis vectors are going to be in this new coupled basis. So let's look at just sort of summarize the basis states we know right now, right? So we have this F squared operator, and when it acts on the plus plus state, we, just by inspection here, we see that gets 2h bar squared plus plus, right? Since F is one of our generalized sort of momentum operators, its eigenstates Fm are going to be F quantum number, F squared acting on its eigenstates is going to be F plus 1 times h bar squared plus Fm. That's the eigenvalue equation for a generalized, momentum operator squared. So in this case, what this is showing is that the F equals 1 for in the coupled basis for the plus plus state, right? And if we look at the Fz operator operating on this plus plus state, we can go way back up here to when we looked at, here it is, that Fz operator. We had h bar, it was just equal to the eigenvalue h bar times plus plus. And again, for the Fz operator acting on Fm, it's a generalized momentum operator. We get that m value h bar Fm in its eigenvalue equation. So in this case, that's telling us that m is equal to 1. So in the coupled basis, we have the F equals 1 and m equals 1 state is equal to the plus plus state in the uncoupled basis, right? This is the, or to write it out more explicitly, ms is equal to 1/2 and mi is equal to 1/2 state. So we've related our coupled to our uncoupled state. We can do the same thing for the minus minus state here, and we get F equals 1 again. It has the same eigenvalue for this. The m value is actually -1. If we go all the way up here, we see that eigenvalue is -1 h bar. So that is our minus minus state, or again, written a little more explicitly, ms is equal to -1/2, and mi is equal to -1/2. So we've related our coupled to our uncoupled basis for those two sort of basis states that are shared amongst those, right? So what about these other two, right? We don't have these eigenvalues sorted out for these matrices just quite yet, right? Because we have these degeneracies and these non-diagonal submatrices in that. So what we have to do that is we have to diagonalize this submatrix to get the relationship between the eigenvalues of this operator and, these basis states, right? So how do we do that? Well, that submatrix, if we leave out this h bar squared now because it's just going to be constant that carries through, we have to diagonalize that submatrix, which involves taking the determinant of our characteristic equation. So we have 1 minus lambda, 1, 1, 1 minus lambda. If we take the determinant of that and set it equal to 0, it's pretty straightforward. We get 1 minus lambda squared minus 1 is equal to 0. This ends up being lambda squared minus 2 lambda, and then plus 1 minus 1 goes away, so that's equal to 0. That has the solution lambda is equal to 0, and lambda is equal to 2. To figure out, so those are the sort of eigenvalues of that submatrix. If we look at the, let's just look at the lambda equals 0 case, then we have, 1, 1, 1, 1 on that, whatever, A sub 0, B sub 0, whatever those, that column vector is for that eigenstate is going to be equal to 0 h bar squared, if I bring back in that h bar squared, A0, B0. This tells us that A plus B is equal to 0, or A is equal to negative B. And, and then if we wanted to normalize that, that essentially is saying that our eigenvector is going to be 1 over root 2 after we normalize it, 1 minus 1. Or written in, since we're in this uncoupled bases right now is what the basis we're trying to diagonalize in. This is 1 over root 2 plus minus, 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 plus. It is that one. Similarly, we can do the same sort of thing for the eigenvalue lambda equals 2. And if we go through that whole process, it tells us that the corresponding eigenvector for that one is plus minus plus minus plus, right? That's that normalized eigenvector, right? Now, if we have these sort of eigenvectors, we can then we can identify what the quantum number, that m quantum number, is going to be for these states, and then we'll have the quantum numbers for a coupled basis and what they equal in the uncoupled basis. Right. So again, we had for the lambda equals 1, that f operator operating on this vector gives us m, it gives us the eigenvector 0. So for this, for this state, we have the f equals 0 quantum number. And for this state, we have the m equals 1 quantum number, right? Because remember, f operating on fm has the quantum, the eigenvalue equation f plus 1 h bar squared operating on fm. So this 2 is actually f equal to 1 here, right? F is equal to 1, right? So we have our quantum numbers for the f that associated with f. We have 2 f equals 1 states here, f equals 1 and f equals 1 for the polarized spins. And in the unpolarized spin ones, we have 1 f equals 1 and 1 f equals 3. So the f values are 3 1s and a 0. And these are going to be our triplet states, and this is our singlet state. What about the m values? Well, we had 1 and minus 1 for these states up here. 1 was 1, 1 was minus 1. If we take this f sub z, remember these m values have to come from the f sub z operator. If we take the f sub z operator and operate on this state, we get a 1/2 and a minus 1/2, right? Because this is sc plus iz. So the sc operator is going to give us a 1/2 and a minus 1/2. And the iz operator is going to give us a minus 1/2 and a 1/2, and these. So this is going to be an m equals 0 state for both this and this eigenvalue. So we have 0 and 0, right? So organizing this nicely, that seemed a little disjoint. In a coupled bases, what we've just shown is sort of the same thing we had in the hyperfine interaction, that we have, so these are written in terms of the quantum numbers, total angular momentum, and the z component of that total angular momentum, or that magnetic quantum number. We have the states 1, 1, 1, 0, 1, negative 1, right? And 0, 0. Those are our FM quantum states in our coupled bases. And in the uncoupled bases, these end up being equal to just plus, plus, minus 1 over root 2. Sorry, I have to normalize this. Plus, minus, plus. The 1 minus 1 state is equal to the minus minus state, and the 0, 0 state is plus minus the anti-symmetric combination of those two unpolarized spin states. And so what we've done is we've related the coupled to our uncoupled bases here. And these are, these should look very familiar if we go all the way to the top. These are the exact states that when we diagonalize the perturbation of our hyperfine interaction, these are the states we got. These are the triplet states, and this is the singlet state. And they are, the total angular momentum quantum number equal to 1 defines the triplets. The total angular momentum equal to 0 defines the singlets. And, we can see, if we look at these, looking at the total angular momentum sort of coupled bases, we have the same sort of things where F equal to 1 defines a manifold of M's that go from negative F in integer steps up to F, right? And for the F equals 0 state, we only have the M equals 0 z component of that. But if we go back to the start of the problem, looking at this hyperfine interaction, and had we acknowledged, okay, we have a conserved total angular momentum, we're going to want to use a basis that sort of matches that, where our quantum numbers are also going to be conserved because they're associated with that conserved property. We could have said, all right, let's use our coupled bases, and this hyperfine Hamiltonian would have been diagonal, and we could have just quickly picked off what those energy shifts were and known we had our eigenstates were just the basis states we were using. We had to go through all this process of diagonalizing these matrices again as well to get there, but it turns out that this is a common process. What we've done is essentially we've taken our coupled bases and we've determined, so we have our FM states, and we know that we can write any state as a linear combination of basis states from any bases. So we have figured out these sort of CIs of, here, let me use a clear thing, a C, M, I, M, or MS, MI, MS, MI. We can write these states as a linear combination of basis states in our coupled, our uncoupled bases. And what we've just done with all this work is figure out what these coefficients are in that relationship, right? That's all we've ended up with here, right? We've determined that, it's 1 here, 1 over root 2, and 1 over root 2, and negative 1 over root 2 are the coefficients that go into the sum. Turns out those have a name. They're figured out for all these sort of angular momentum systems, and how to add them together. They're called Clebsch-Gordan coefficients, and they're so common and they're so useful. They're typically just listed in tables. Given certain angular momentum, if you're adding angular momentum from of two different objects. In this case, we were looking at an electron spin and a proton spin. We know the individual spins of those, or the individual angular momentums. We can write a coupled that in terms of, a total angular momentum of that system using those Clebsch-Gordan coefficients. And they're looked up, and typically you can just look them up in tables rather than doing all that work. Next video, we're going to go through that process of general addition of angular momentum and sort of see how we would come up with the Clebsch-Gordan coefficients and how we would make one of those tables, and then just how to use those tables in the future. For now, just summarizing what we've done, we were looking at what makes a good basis, right? In the hyperfine interaction where we had A over h bar squared s dot I, this was sort of our motivation for looking at this. We realized that sort of total angular momentum of our spin and electron system, or our hydrogen atom, was going to be conserved. So we wanted to use a basis that had that was associated with that total angular momentum, that conserved quantity. And we figured out how to write, those states in terms of the uncoupled bases that we were familiar with. But when all that was said and done, using that coupled bases, we're now in a position to just show how much simpler solving this perturbation would have been, right? We have, we defined f as s plus I, so f squared is just s squared plus I squared plus 2s dot I. So this s dot I part of our operator is just going to be f squared minus s squared minus I squared all over 2, right? And in the Fm bases, so using our f equals 1, m equals 1, and our 1, 0, and our 1, negative 1, and 0, 0 Fm bases, every one of these operators is diagonal, right? So this, our perturbation Hamiltonian ends up being just A over 4, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, negative 3, right? And you can get that just, to be clear, what is f squared minus s squared minus I squared acting on, say, our 1, 1 state, right? Well, this gives the eigenvalues. Well, f squared has the eigenvalue of 1, it's f plus 1 times h bar squared. Minus s squared is going to be minus 1/2 times 1/2 plus 1. Same thing, h bar squared, minus 1/2 plus 1 for the nuclear spin, because those are both spin 1/2 systems. This whole thing, if we plug in f equals 1 and s equals I equals 1/2, this whole thing ends up just being, excuse me, this is equal to 2 minus 3 over 4 minus 3 over 4, which ends up being equal to 1/2. So pull out the 1/2 up here, and we get this matrix. But anyway, going through this though, now that we have our hyperfine perturbation matrix in matrix form in this FMC, we see it's diagonal. We can pull off the eigenvalues right away, and we know that for the 1, 1 state, we have an eigenvalue of a over 4, or a matrix element of a over 4, so we know that's the energy shift. Likewise for the 1, 0, the 1, negative 1 states, and then for the 0, so for the 0, 0 state, we get its energy shift is negative 3 over 4a, right? So 1, 1, 0, and 1, negative 1 states all have that energy shift. So really quickly, knowing that we had to use this bases, we can solve our hyperfine perturbation. The thing that made it, that allowed us to identify it was a good basis to use, was that total angular momentum is conserved in the system we're looking at, so we want quantum numbers associated with that. Anyway, hopefully you followed this. Again, next video we're going to go through just the general addition of angular momentum, not just a 1/2 electron spin and a 1/2 nuclear spin. We're going to look at just in general. If you have questions on this, email me. Let me know. Bring them up in the synchronous sessions, and hopefully this will start to make sense and we'll get really comfortable with it. See you then.